Awesome. Thanks for having us here today. Super excited to talk about this topic, something very near and dear to my heart as well as Hubert's, so we'll dive right in. We're going to be covering a lot of stuff, but we're hoping that this reaches a wide audience, so there should hopefully be something here for everybody. We're going to go briefly over what branch is, so it puts into perspective the infrastructure that we've built out. We're going to do a brief introduction to containerization, and then we're going to move into applications of Kubernetes. We're going to go through a couple examples. If you've never heard of Kubernetes before, that's perfectly fine. You'll walk away from this talk hopefully as an expert. We're also going to talk about something that I'm very passionate about, which is cost management on AWS. I think there's a lot of small startups here that are just starting to get onto the platform, but we're going to look at what it could actually be managing, a multi-million-dollar AWS budget. And then again, at the end, we'll talk about Q&A. So this talk is intended for a wide audience, as I mentioned. If you're a founder or maybe a budding founder or CTO, you'll take away some lessons and strategies about cost management, about scaling infrastructure, and some of the decisions you can make there. If you're just a hacker, a developer, an engineer, and you want to learn about some cool technology, you will learn about applications of Docker, applications of Kubernetes, as well as various AWS features such as ASGs. And then lastly, if you are here because of the really awesome pork tacos and you're just kind of chilling out here, hopefully you get exposed to some interesting new technology and terms and have fun in this talk. So really briefly, I'm Ian Chen. I'm the Director of Engineering at Branch. I'm with my colleague, Hubert Chen. He's the manager on the infrastructure and operations team. And we've both been with Branch for about four-ish years. The company itself is only 5 years old, so we've got the opportunity to see all sorts of interesting, rapid hyperscale that our startup has had the great fortune to go through. So let's actually quickly talk about Branch. If you've never heard about Branch before, we're a startup. Our head office is in Redwood City. As I mentioned, we're about 5 years old, so founded in 2014. We're a mobile deep linking analytics and attribution company. We have about 250 employees, about 70 engineers. We have about 45,000 customers and apps using our core product. And we have about 12 offices around the world. Not going to go into too many details about how Branch works, but if you are in the app business, if you have a mobile app, if you're a marketer, if you're in the growth business, and you've never heard of Branch, you should. You can learn more about it later on. You can talk to us afterwards, but we help customers grow their user base. We help them with their analytics, their reporting, and as I mentioned, their deep linking. And just a smattering of some of the logos. We work with some of the biggest companies in the world, including Amazon, to provide them their analytics and reporting. And again, this is all setting the context for some of the scale that we have to manage and deal with. So speaking of scale, let's talk about some of the numbers that we've had to overcome and some of the scaling challenges that we've engineered with or around over the last few years. Today, our core platform sees about 12 billion transactions per day. Any given time, we can burst up to about 250,000 messages per second. Within our infrastructure, we have over 100 microservices running in our production environment. We started very typically with a giant monolithic JavaScript application, but we actually decomposed that into microservices back in 2015. We've been operating Kubernetes in production for over 4 years now. And we have about 70, as I mentioned, software engineers that on a day-to-day basis are deploying tons of changes. So it is a pretty substantial management and governance challenge. So the two different challenges that I'm actually going to speak to today, and we hope that you get some answers to by the end of this talk. So one is the challenge around general compute. I talked about 70 engineers is not actually that many compared to some of the other bigger companies in the Bay Area, but we wanted to provide a flexible, repeatable compute platform for our growing eng team, our growing scaling needs, and the needs of our developers. So some of the challenges that come up on a day-to-day are things like we support several different languages within our production infrastructure. Java, Python, JavaScript, and the developers want to deploy their services in a scalable means as fast as possible. And part of our job as infrastructure engineers is to provide them the platform so that they can do that. We also don't have a very big infra ops team, so we can't have a DevOps or an SRE paired with every developer. And each developer might themselves own 5 to 10 services or more. So you're talking about hundreds of services running in production, all needed to keep this platform online. So we'll talk about the challenges and how to overcome these compute challenges. The next is costs. So none of this is going to be free. As your infrastructure grows and scales, so do the costs. And forecasting the costs can be quite challenging. Predicting these costs, forecasts are generally going to be moving slower than a rapidly iterating development team. And there are a lot of different products that Amazon offers that make cost modeling and purchases more flexible, but they're non-trivial to implement very well. So I'll provide some tips on how you can do that as well. So the underlying principle behind a lot of this talk today is this core concept of taking an application runtime and having it run on an instance somewhere. So the very canonical basic example is a developer writes a simple Hello World app. And on Amazon, you could provision an EC2 instance and then deploy your workload to that instance, and then now your application's running, and everything's great. And I wish it was that simple as we scaled, but the reality is we have, as I mentioned, hundreds of developers deploying hundreds of services. Each service has hundreds of replicas running, and those hundreds and hundreds of runtimes are also themselves running on hundreds of instances. So this dependency graph and that simple runtime to compute concept gets very complex very quickly. And Kubernetes and some of the other technology that we're going to talk about today are some of the ways that we've managed to overcome these challenges. And the core objective that we have as an infrastructure offering is we don't want our developers thinking about what instances or what machines their code is running on. They just want to take their code, deploy it, and then move on to the next feature or the next set of tasks that they're on. We also don't really want to be thinking about the very, very specific details of perfectly provisioning each specific deployment. I might know that this JavaScript app only needs 2 cores, and then as that scales, I can scale it up to 3 cores. But the task of budgeting that, purchasing the instances can be pretty cumbersome over time. So we really just don't want to think about it. And again, we'll dive into that. And at a very high level, this is the end stack that we work with. And we're going to walk through each component of this infrastructure. I'll describe it at a high level, but my colleague Hubert will actually dive into it. And this is really what we're trying to achieve. At the very top, we have our application workloads. These are programs. These are software systems that our developers are building. We deploy them in Docker containers on top of Kubernetes. We use a blend of the various purchase options that Amazon affords us when we deploy these onto EC2 instances. And it's a nice and convenient diagram here, but there's a lot of nuance and a lot of detail here. But again, the end objective is to solve those 2 original goals. 1, how do we solve scalable compute? And 2, how do we do that in a way that's being very mindful of costs? So let's dive into some of the technical details here.
OK, thank you. Thanks, Ian. So let's talk about containerization and orchestration. So containerization came about relatively about like 10 years ago-ish. Really been popularized by Docker. And for a long time, it's been used in very high scale, very large workloads. And as a variety of developers have realized the power of Docker and containerization, it's really grown pretty dramatically. Actually, let me poll. How many of you use containers? How many use ECS? Oh, sorry, EC2? Pretty much everyone. Kubernetes? Some. OK, good. So some of this will be reviewed for people who have used Kubernetes, but I'll go into some advanced topics, particularly on scheduling. Containers at a basic layer, they provide isolation between processes on a Linux host typically. So that means when you run two processes, you can be pretty much guaranteed, two containers on a Linux host, you can be pretty much guaranteed they won't interfere with each other, which is really, really huge from the standpoint of making sure that your applications don't collide or cause any problems. And that means you can run them much more reliably and much more scalably. Containerization particularly shares, unlike virtualization technology, which essentially you're running your own kernel, containerization shares a kernel with potentially other containers. The two big advantages of that is that means the startup time is faster because you don't have to spin up a new kernel for each instance or container you're running, and the memory footprint is much lower because you're not, again, running the same kernel. The downside is you're restricted in terms of what you can do within the kernel, and you don't have a full feature. Like you can't run both a Mac container and a Linux container on the same machine. That doesn't really work that way. But the advantages are very significant for large-scale environments because the memory efficiency and the startup time are really, really powerful, especially for scaling big things. The efficiency allows you to really, really pack nodes and instances very tightly and put in a lot of instances. So we have many, many nodes which run 20 plus containers. And they're not huge nodes, but like 16 cores, you could run 20 containers on easily. And in a traditional like on-prem world, you would also, without containerization or virtualization, you'd essentially buy a whole host for any kind of workload. And that was very expensive, and the utilization was not very good because you were over-provisioning so much. The other benefit of containerization is the consistent and immutable images that you build to do it. So I spent a lot of time in the on-prem world trying to figure out, oh, why is this one server different? Maybe I deleted a file that I needed, and then I have to redeploy and re-image. And that kind of problem really goes away when you're taking containers to their full power. Because you just say, OK, I'm going to deploy this one container everywhere, and it's always the same. You never worry about this sort of a snowflake problem where one server just starts to look different. Building the consistent images is really, really great for large-scale production environments. And finally, what Docker really brought to the table was a great tool set around building images. So instead of building up 20 different Linux hosts of Red Hat and Ubuntu and not being sure if they're the same, the tool set around Docker allows you to say, OK, all of these 20 images are all the same, and we have perfect consistency. And I can deploy it on my desktop. I can deploy it in my production environment. I can deploy it in staging. And they always, like, I spent a lot of time in earlier iterations of my life debugging developer laptops. And that's just such a nightmare. I'm never going to do that again. So among those things are the consistency is really, really powerful for test environments. So what does Kubernetes bring to the table on top of that? So now that I've explained Docker a little bit, Kubernetes is essentially an orchestration layer on top of Kubernetes that allows you to manage large numbers of Docker containers. So it's not too difficult to manage 3 to 5 hosts of Docker containers. You just deploy to all the hosts, and then you say, OK, point my web server to this host and this container, and point my database to this container. But Kubernetes provides a lot of tools around managing large-scale workloads. So if you want to spin up 100 replicas, that becomes a big challenge, particularly in scheduling. So where do I have the resources to run these containers? And service discovery. Service discovery is actually quite a tricky challenge. Like if I tear down a container and I move it from one host to another, how do I fix the references that are talking to that old container such that they're now talking to the new running container? So that's actually one of the greatest strengths of Kubernetes, and feel like they've done a very good job of satisfying dynamic workloads such that when things move, that you automatically get pointed to the new correct versions. As I mentioned, highly dynamic environments are really where Kubernetes is very strong. It's particularly useful with small microservices. It's not so great with large like database or compute-bound workloads and other types of things where you really want, for instance, very specific types of requirements. Like you need to occupy every single core on a CPU, or you need to run a high availability database and you need to talk to storage. Those kinds of workloads are not as great for Kubernetes. Kubernetes was really designed for small microservice workloads in dynamic environments. And finally, it manages deployments as you say, OK, I want to deploy to 20 different machines. I want to deploy 100 replicas. It takes care of that. It has a lot of primitives around managing that so that it rolls out smoothly. It doesn't crash. It restarts automatically. If your container crashes, Kubernetes takes care of it and restarts it and can manage it for you. If it crashes permanently, it can reschedule it to a different node. Most of you are familiar with EC2. Almost everybody uses it. We're all in the AWS loft, so I'm sure you're familiar with the Elastic Compute Cloud. It provides, as far as we can tell, nearly infinite scalability in terms of types of instances, number of instances, costs, and a lot of features that you don't have to worry about. Like, is the network solid? Like, AWS's network is incredibly solid. Like, a lot of these things, that's why we're in the cloud. We don't. Most companies are moving from on-prem environments to cloud environments, and AWS is probably the best choice. As much as we would like to try other on-prem instances to save money, but AWS is still gives us the best flexibility in terms of choice of instances and global locations and various other cloud integrations like their CloudFront, their ELBs. All of those feature sets put together are pretty strong offerings. So applications. So when you provision a Kubernetes cluster, you can kind of do it in two different ways. First, you could think of it just like a traditional on-prem environment where you have whatever, 20 instances, 20 nodes, and you just install the Kubernetes binaries on it, and you just run them. That works, and you can definitely, there's lots of tools to do that, and if you have a very static environment, it works. But you don't get the benefits of really using the cloud if you just sort of, if you're provisioning an instance yourself, and then you're installing Kubernetes binaries on top of it, and then you're having to join the cluster. That's OK, but it doesn't take advantage of the full advantages of the cloud. Things like autoscaling, and that's what I'm here to talk about primarily. The autoscaling features, once you do a cloud native install, are pretty strong, and I'll go over some of those. It'll do things like, OK, Kubernetes node joins a cluster, and then new workloads get scheduled onto that node, and then that node automatically, those workloads automatically join load balancers, and then it can take care of all of that for you. And so doing a true cloud native install is definitely highly recommended. And
one of the points that I wanted to dive into a little bit more, especially for those that aren't too familiar with Kubernetes, is, again, this idea of providing a generalized compute platform. So in this really, really high-level diagram, at the very bottom, we have an example of provisioning 3 EC2 nodes. We have an M4 4XL, which has 16 cores. And then let's say we throw in 2 more M4 XLs, which each have 4 cores. When we're talking specifically about EC2, we're interacting with 3 unique instances. And when we set up Kubernetes running on these 3 nodes, the Kubernetes cluster exposes this effectively as 24 cores. And for the developer that's deploying their system into this cluster, they don't know and they don't need to care about how many instances are under the hood. So obviously 24 cores is great. In our production environment, we're talking about tens of thousands of cores. But again, we're starting to see that abstraction and separation of the developer's concerns of, I need some cores, and the infra team's concerns about how many EC2 instances is this actually running on.
So the scheduler, to land workloads onto instances, one of the very core components of Kubernetes is a scheduler and how it takes care of workloads. So you can see in this diagram the 16-core M4 4XLs and the 2 4-core M4 XLs. So if you look at different types of workloads could have an ideal fit on various different instances. Like in the worst case, and I've seen this happen in like on-prem environments, you have an instance with, say, 16 gigs of memory. And then you have an application which uses 9 gigs of memory. So you've now stuck yourself in a terrible position because you're wasting 7 gigs of memory on every single instance. You do this like once, it's fine. You do this 100 times, it just gets wasteful. So being able to schedule and finding the places that you can fit your workload is really, really important, and is the way you maximize the compute and memory efficiency. The scheduler also has a vast array of more complex resource constraints. Among them are things like, so CPU and memory are very basic, that everybody understands them. You say, okay, I need 6 gigs of memory, I need 2 cores. Those are easy. But the scheduler also has a lot more features around things like affinity. For instance, you said, okay, I have a workload that runs on this node, but I don't want it to run on this. I only want it to run once here because it's like a database and I'm replicating it to somewhere else. So the scheduler provides features to Kubernetes users that say things like anti-affinity. They say, don't schedule these together because that's going to compromise my availability if I lose one. So there's a lot of different other kinds of ways. And sometimes you want to co-locate them. You say, OK, I need super high performance between these 2 applications, so I'll co-locate them with the scheduler's affinity feature. And then persistent volumes are very tricky to manage. Whether you're using EBS or some kind of external storage, the scheduler can understand that, OK, I have an EBS volume. I need to mount it to another instance. If my instance dies, I can reschedule my pod, and then I pull the storage back onto that same instance. That's a really, really powerful ability, and it's not easy to do. And finally, you can request specific types of hardware. Like I could say, OK, my pod needs GPUs. And now that's not a thing you just always get with an instance. You have to provision a special instance. But the combination of the Kubernetes scheduler and the autoscalers will allow you to do that. You say, OK, I need 100 GPUs for this workload. And if you put these pieces all together in the Kubernetes and in an AWS environment, you can get that. And you could say, OK, these workloads, I'm going to spin them up for 20 minutes, and then I'll tear them down when it's done. Those kinds of things are really going to help you manage costs, especially if you can use spot instances as well as in combination with on-demands and reserves. This is one thing I kind of like to show. One of the things I'm proud about in how we've used Kubernetes is the efficiency we've gained out of locating all the workloads on a few very large, dense nodes. So when you start out, just provision an instance. You just say, OK, give me a 4-core, 16 gig and 4XL. And then you say, OK, my Java process, let's put it on there. It's going to take 2 cores and 8 gigs of memory. But now you've wasted half of that. But once you start to take the power of the containers and you use the scheduling on top of it, and Kubernetes manages all the scheduling, then you can really pack those things tight. So you could say, OK, now I'll pack 2 of these 2-core 8 gig processes onto the same 4-core 16 gig and utilize it perfectly. And then you can also do reservations to say, OK, I may not use it all the time, but I'm going to burst up, so I don't want you to schedule too much on those things. So one of the things I'm proud about is how much we've improved the efficiency, because it's not uncommon for typical enterprise workloads to have just 10% of CPU utilization or less, especially like a database where you can't reprovision it. It's got a very low utilization rate during normal, and you've just provisioned for these massive spikes. So you run it at 5% utilization all the time, and then like once a night during your hourly batch jobs, it goes at 80%. So improving the efficiency is one of those things I'm really proud of that Kubernetes has done. So if you look at those numbers, like this is actually low traffic, where we're hovering at 20 to 50% utilization. During peak traffic, we'll go to 60, 80% plus. So let me talk about the actual auto-scaling features of how Kubernetes works. The very simplest one is the horizontal pod autoscaler. Has anybody used this? Anyone? OK, good. So the horizontal pod autoscaler is relatively simple and straightforward as it starts. So it measures the CPU utilization of your processes, your pods in Kubernetes world, or replicas. And then when the CPU utilization goes high, then it can spin up more replicas. It's a simple linear calculation where it says, OK, I have a target of, say, 50% utilization, and after that, my workload starts to fail or performs poorly. So if I say, OK, I want to use 50% of my CPU, then when it gets to 100%, it would scale to 2 and then attempt to split that workload. And that's relatively straightforward. It just does a CPU calculation, and every few minutes it can scale up or scale down and just add and subtract new replicas. So if you, so the workloads, when the workloads exceed a target threshold, then it can scale up, or when it falls below, then it can scale down. You can also specify a minimum. For instance, if you have a large burst workload that it's not instant. It takes a couple minutes typically, and you don't want to have to provision every single minute anyways, because the scale up and scale down for most applications is a little tricky. So most of the time it takes 2 to 5 minutes to scale up or down to make a change. But if this is an example of what we do in production. So this event capping service has 30 replicas of a relatively simple Java service, but we run a lot of copies of it, and its target CPU utilization is 75%. So when it hits, if there's 30 replicas and they're all hitting 75%, then or when they start to go over 75% CPU utilization, it'll start to scale up, but it's capped at 50 replicas. So it could go to 100 or 150 once it hits that replica cap. Actually, back up. There's also features that allow you to define, CPU is the most straightforward and easiest metric for which you can scale on, but that you can also use custom metrics in later versions of Kubernetes and say, okay, I don't really care. CPU is not a bottleneck, which it almost never is anyways. Most applications are either memory bound or network or IO bound. So you could say, okay, the IO on my machine is too high. I've defined this custom metric. It takes a little work to plug these in, but not a lot of work. And then it says, okay, now when my IO utilization is 50%, then I scale up or something like that. So it's pretty flexible from if you want to start to define custom metrics, but it'll allow you to get there. Okay. The cluster autoscaler. So the cluster autoscaler, the horizontal pod autoscaler is straightforward and the simplest thing to do, and is what everybody starts out with. The cluster autoscaler is more complex. So the pod autoscaler assumes that you already have the nodes that you need. So if you've already maxed out your whole cluster, it can't do anything. It won't schedule. It doesn't know where to put things. The cluster autoscaler alleviates this problem by saying, OK, I can grab more nodes or instances. This works both in AWS and GCP, and also Azure, and I think even DigitalOcean may support this. But it's really powerful. So now you can actually take full advantage of the cloud. Like horizontal pod autoscaler is something you would use even in an on-prem or local environment. But to actually get the utilization that you want out of the cloud and be able to scale up instantly to unlimited size workload, you could use the cluster autoscaler to add nodes to your cluster. So the cluster autoscaler presumes that you have sort of this cloud environment and your nodes just can start up and join the cluster. So that's why I really encourage people to set up sort of cloud native environments of Kubernetes. And once you have these autoscaling groups set up and your nodes can just join your cluster properly, then whenever you have scheduling problems and the cluster autoscaler can detect that your pods are just stuck pending because they can't be scheduled because there's not enough resources, it'll go through and it'll detect that and it'll figure out which nodes it needs to add to your cluster in order to get the nodes that are waiting to schedule scheduled. Now, obviously, this takes a minute or two as it detects AWS instances and figures out which one it needs, and then it spins them up, which can take 30 seconds to a couple minutes, depending on the type of instances and your startup process. But it's really, really powerful, and it allows you to, at the cost layer, you don't pay for pods or workloads. You pay for instances. So this is how you actually control their cost in conjunction with pod autoscaling or other autoscaling types of technology. It's actually very interesting because it runs its own copy of the scheduler. So if you say, OK, I only want GPU instances for my workload, then it understands that and says, OK, I'm not going to spin up these regular M4s because they don't have GPUs. I'm only going to, if you have an autoscaling group that has GPUs enabled, then it would spin up those specific types of workloads. So it's very powerful. So that means you can run mixed workloads. You can do all kinds of things. So it also understands multiple different types of autoscaling groups. So if you said, OK, I have this GPU cluster, GPU autoscaling group, and I also have a regular workload, but it can choose between them for those situations where you need GPUs, but maybe it would choose the regular for your normal workloads. And this is generally all configurable.
Yeah, and I'd say on a daily basis, I described our day-to-day traffic of, let's say, 250,000 messages or events coming in per second. Due to the nature of our product, we have a very predictable sine wave of traffic where there's troughs and peaks depending on the activity on the internet. And as such, we could track the metrics of our Kubernetes cluster growing and shrinking automatically every single day. And this is without the input from anybody on the infrastructure team, hopefully, but it's just growing and shrinking accordingly, which is great from a cost management perspective. Similarly, and that's in the context of the cluster autoscaler, going back to the pod autoscaler, we might have a certain system or a certain endpoint that has a sudden burst of traffic. Well, the pod autoscaler will automatically detect that spike and then scale itself out, even if we don't need to scale out the entire cluster. And a lot of this stuff is happening automatically under our feet. It's happening at 2 in the morning when hopefully we're sleeping, or it's happening at noon when there's a big burst of traffic. And again, these are some of the underlying benefits that we're getting by using these tools.
Finally, and this is a relatively new feature, is the vertical pod autoscaler. So the vertical pod autoscaler is actually has a different theory. It measures what your pods or workloads are doing, and then it scales an individual pod to the right size after it measures it for a while. So you run it for a week and it says, okay, you've allocated 2 gigs of memory and 1 core, but you're only using a half a core and 1 gig of memory. So I'm going to resize your pod such that it can only take advantage of that those sets of resources. And then you can tighten up your bin packing, your resource utilization. It's not as commonly used, but it is a new feature, and I expect we'll be taking advantage of it soon. And many large workloads would benefit from this. It takes the worry of how to, like, we don't want to measure we don't want to make human decisions about every single workload and how much memory it needs and how much CPU it needs. But this will help take the decision making out of our hands and just sort of do it algorithmically. What do we do at Branch? So at Branch, we have half a dozen clusters running medium to plus size cores. There are companies that run 1,000-node clusters. I don't recommend it. It can be quite challenging. Our clusters I would call them medium size, 20 to 150 nodes. We use plus size instances, I would say. We don't. For most of the scheduling features, it's probably better to use larger instances that allow you to pack them tighter. If you use smaller instances, you'll get into the problem that I mentioned about where you have a 16 gig machine and you try and run a 9 gig workloads and now nothing else can schedule on it. It also works better if you have smaller workloads. So instead of running 5 large 4 gig Nginx pods, you run 20 1 gig Nginx pods or something like that. So smaller workloads tend to pack better and they're more efficient. But sometimes that your application doesn't work that way. But that's a consideration. So we run 16 core to 128 core type of machines, and we have hundreds of these. The network technology we use, we actually are trying a variety of different ones. The simplest one is the KubeNet one. So that essentially leaves all routing decisions to AWS. That's straightforward and has been quite reliable for us. There's a limit to the size of a cluster you can build with that, though. But we've also tested Weave and KubeRouter, and we're going to test the AWS VPC CNI. For our costs, we try and use a variety of different methodologies, and Ian will go into these a little bit more. But part of it is balancing the availability of on-demands, which they will never take away, versus spot instances, which you can lose at any time. And it is a danger that we have encountered where the AWS will decide, OK, these spot instances are ephemeral, and you lose 30 at a time. And we've lost, I don't know, more than half of a cluster at this due to AWS taking away spot instances. So but the cost savings are huge, right? They're 1/4 of the cost of the on-demand instances. So we try and mix a balance. For our baseline workloads, we have somewhere between 50 to 80% sort of on-demand instances, and then we use spot instances to fill reserve capacity. Let's see. So another thing we do is we kind of mix, we're trying to provision, we have different SLAs for different clusters. So we have a high SLA cluster where you really don't want to lose your workload. You never want it to get put on a spot instance. And then we have our other workloads where, okay, you can burst to 600 cores if you want. We have large Spark job and large batch workloads that we'll just say, we have full auto scaling and say, okay, you can run the biggest job that you can possibly imagine, but there's a reasonable chance you might get interrupted, whether it's due to spot or cluster or something else like that. So but because we're using spots in those clusters are much cheaper to run than the on-demand sort of high service level agreement type of workloads. And the tooling is done with Circle CI, which is our deployment tool of choice, and Flux, which is a GitOps tool where it says, okay, let's check all our deployments and all our configuration, our Kubernetes configuration into Git, and then Flux just automatically applies them. That gives really good visibility to developers, operators, and everyone to say, okay, this change went out into the cluster at this time. It caused these issues or went out fine. So deploying. So one of the key things I would say about trying to run Kubernetes in a production or large scale environment is Kubernetes is actually pretty straightforward once you sort of get into the flow and sort of understand the primitives and the objects. But building your workloads to actually deploy and have the CI process, the continuous integration and continuous deployment process, that's actually quite hard. We spent probably as much time or more time on continuous integration and continuous deployment as we do on Kubernetes management. So CI/CD becomes quite tricky because you have to support multiple platforms, whether the Node.js compilation environment is different than the Java and Maven, and it's a per platform. We try and make them generic within a platform, of course. We always use Drop Wizard, we use Nginx, but there's almost always some custom work going into deployment and continuous integration to get the whole thing to build. But once you get the whole thing built, then the deployment is not super tricky. GitOps is sort of this new methodology that everybody's taking on where even configuration and code changes are, not just code changes, but configuration and management and tooling changes are all checked into Git and deployed automatically. So the only interface or the only way you ever make changes should be through Git or your source code configuration, source code management tool. And that means you can always roll back. Some things don't roll back, like if you delete instances, that's not something you could roll back, but you can always track changes as well and make sure that because they all went through the same pipeline of deploying infrastructure as code, then you always know what happened. And the other thing is building a pipeline of this type makes it so that you can unify and start to codify things. So now I don't have 5 different interfaces to make changes to our monitoring system. I change it once in Git, and now I can automate the change in front of that. So I can build a tooling pipeline in front of that. So all it has to do is push to Git to get my monitoring changes in. That's not Kubernetes specific. That's just general good practice. OK, moving on. So what are some of the tips that I would say to people starting out with Kubernetes or building new infrastructure with Kubernetes? First, and this is just good practice, Kubernetes or not, is build stateless whenever possible. Stateless applications will give you much better scalability, they'll give you much better reliability, and it'll make deployment and management a lot easier. Kubernetes moves very quickly in terms of the community. And one of my regrets is I didn't build a way to upgrade Kubernetes clusters very easily. So now I'm kind of stuck with some old clusters that I have difficulty managing, but I want all these new features with 1.11, 1.12, 1.13, 1.14. So the community adds tons of features very, very quickly. So have a process by which you can upgrade your cluster to get all the latest features, because nobody ever builds for 3-year-old version of Kubernetes. It's probably a mistake to start putting your most critical workloads into Kubernetes. This is obviously just safe and sound practices, but people try and be aggressive about putting databases into Kubernetes. I wouldn't do that. So I guess when somebody asks me, should I put my database into Kubernetes, I say, well, how many nines do you need? If you need 2 nines of availability, if you're 99%, yeah, it's probably fine. If you need 4 nines, you should rethink what you're doing. Like if you only want to survive 5 minutes of downtime a year, then I would not put it in Kubernetes yet. I could see a future in 2 or 3 years where that's possible, but like it's not that risky. It's not worth risking your business for. And finally,
specifically databases.
Databases, yes.
Yeah.
Databases also have very specific high I/O requirements, high network requirements, and all these things. And you don't really want to co-locate your databases with all the other things that can make it noisy or problematic. And finally, bigger nodes for cost efficiency, but satisfy your availability requirements first. I typically say run 5 nodes in a Kubernetes cluster, then you have a core system like a Kafka or a Zookeeper where you need 3 nodes available. As you grow, you'll expand the clusters and you can upsize. For efficiency, you should use bigger nodes, but make sure you have the availability that you need first, because sometimes, like if you ask for 2 M4 XLs, they could actually be located on the same machine. So that's one of those dangers about availability and understanding where you should cut corners. So what are some of the easy things and hard things about running Kubernetes? Like in a cloud-native environment, it's pretty easy to change your instance types. Don't get tied to say, oh, I have these M4s and I like them, or almost all of the cloud-native environments, you can swap out your instance types. If you run out or decide that instance type is either too slow or doesn't work for your application well, those are relatively easy to change. Most of the deployment and management tools allow you to swap out different types of instances. You might need to build a new MI, but it's not that bad. And as I mentioned, deploying applications onto Kubernetes, the most powerful thing about Kubernetes is from top to bottom, it has very good APIs. Whether you want to just send it in a YAML text file and deploy it, or you want to build a Python or build a Go client that talks to the API server and really fully orchestrates your system. But all of the APIs are very good, and they have a full path to upgradability and manageability. And finally, one of the things that I think was very successful for us was getting our developers to understand the Kubernetes environment and why and how workloads work in it. And I think it's been a very big productivity, and it's a skill that understanding reliability and scalability was good for them. Now, the things that are hard for them, hard in the Kubernetes world, is certain types of things like changing your network type. That's a decision you should make very carefully. We luckily chose the right one with our first production environment, the Kubernetes, the AWS native routing. But I've had to destroy clusters because we decided the type we use, which was Weave or kuberouter, wasn't as solid as our kubenet cluster. And I mentioned talking about building scalable CI/CD pipelines. Those are application specific, but you'll want to get the whole flow, but it'll pay off once you have the reliability through your deployment pipeline. One of the challenges we had was trying to do the full auto-scaling. Like I mentioned we lost 80% of a cluster with auto-scaling and spots. If you're going to do that kind of workload, that's fine. I think it should be able to support it, but do it, test it. We've had problems with the network scaling, and that's one of the biggest challenges. If you add 100 nodes to a cluster within 3 minutes and then tear them all down, and you can do that 50 times, then your network is pretty solid. The cluster addition and subtraction is very stressful on the network interfaces, but the network technology, but test it, because you will potentially run into problems. And I mentioned don't run a database in it. I think as long as you set your expectations properly, you can run a database, but don't go crazy. And log management is just one of those things we have. I think that's a little bit more of a branch-specific thing. We just have a lot of logs. All right, sorry. Finally, this is my last slide, and then I'll hand it back to Ian. Sorry, I'm running a little slow. How would I compare EKS to various other Kubernetes deployment methodologies? EKS is a fully managed Kubernetes environment, which is very nice from the whole fully managed standpoint. So they do a lot of things for you. They take care of the control plane. They take care of the masters. They take care of the etcd. Those are all good. I'm most concerned about the network, so because that is affects your whole cluster stability. Like individual nodes, they're stateless. I don't care. I tear them down all the time. But if your network gets unstable, then it's very, very challenging. So I like it for the AWS CNI VPC, and I like it for the managed control plane. But conversely, it's still relatively new. You don't get a lot of the newer features because they don't run the very latest versions of Kubernetes, and you don't get a lot of choices around certain types of things like the network, which is good from the standpoint as long as they're taking care of it for you, you don't have to worry about it. So we haven't actually deployed production EKS clusters, but I'm thinking in the next iteration that we will, because we started relatively early before EKS became a thing, but now I think it's almost solid enough that we'll be trying it. And with that,
great, awesome. So Hubert talked a lot about how to leverage Kubernetes, how to set it up, some of the flexibility. I'm going to kind of go to the other side of the equation. I'm the guy that has to pay the bill at the end of the day. So I'm going to talk about what that looks like from my side, some of the strategies that we've taken, and some of the long conversations that I've had with Hubert when designing and architecting these clusters. So the first thing that I'll mention, independent of Kubernetes, is just the EC2 pricing model. Hubert alluded to it earlier on, but the typical model is the on-demand, where you're paying, I think it's billed by the second, but let's just, for this example, use the per hour price. I picked a very standard M4 X large instance. We probably have several hundred of them running in our infrastructure. That simple unit has 4 vCPUs, 16 gigs of memory, and pricing according to US West 1, I pulled these numbers down today. Per hour, you're looking at about 23 cents per hour, which is pretty good. RIs, or reserved instance, is a methodology that we use where you can pre-purchase the instance for 1 year or a 3-year term. And if you do that for 1 year, the price drops down to about 15 cents an hour. And if you purchase it for 3 years, so you're committing to use that instance for 3 years, the price will drop down to about 10 cents. And then the last methodology for purchasing instances is spot instances, if you're not familiar with that. I know Hubert mentioned it several times. Amazon provides effectively elastic marketplace of spot instances that are available to you, but they don't have the same guarantees of availability, in that you may get preempted and warned that the node will disappear in a minute, get off of the node, and then they take it back. But those spots come with the upside of price. We've gotten it down all the way to 6 cents per hour. So you can see a huge price differential between these different purchase options. So if we look at and this is actually, I pulled this from our last board meeting, so these are like legit slides, minus I think I took away some of the prices. You can see that we're spending a huge amount on EC2. So some of the other services here are CDN usage. We use S3 quite a lot, and then there's a bunch of other AWS services that we use. But whenever I talk about cost modeling and cost strategies, I always like asking folks to look at what their biggest costs are. And for us, it's very clear that EC2 and just pure compute is where we're spending most of the money. So this is where we should be spending most of our time optimizing our costs. If you're responsible for managing a large AWS bill like me, this is probably a pretty familiar UI. If not, this is Amazon's Cost Explorer tool. I blurred out like the y-axis in terms of how much we're spending. Maybe we'll talk about that privately after this talk. But I think I left, yeah, I think that if you have it reduced it down to cost per millions, I hope that none of you have to deal with that, but it's a very interesting challenge, and come talk to me later on and we can talk about our strategies here. But this is a view that I've set up and I found to be extremely effective. In the very top left, you can see, well, you probably can't see it, but I've enabled to do a group by the purchase option. And then the 3 different color codes here are purchase option by spot, purchase option by on-demand, and purchase option by RIs. There's actually a 4th color for unused RIs, but we have 100% utilization. So this is the way that I make sure that our pricing, as well as our purchase options, is being well managed. And along the right side, again, if you're a nerd that spends a lot of time in a Cost Explorer like me, some of the other tips that I'd have is when you enable a filter on EC2, and also you filter the usage type by running usage, you'll also get that secondary graph at the bottom, which shows the compute hours per month juxtaposed to the costs. And you'll be able to download this information, import it into spreadsheets, and do whatever kind of analysis that you want. But I use these views to both look at what our costs look like month over month, but also look at the distribution of the usage in terms of CPU cycles to get a good sense of what's going on. Lastly, the very bottom arrow I pointed to is a feature that the Cost Explorer team, so kudos to them, added in recent months, where you can also show the amortized blended costs. So if you are doing 1-year reservations or 3-year reservations, the amortized cost of 1/24th or 1/12th or 1/36 will automatically get blended into these so that you can actually have month-over-month accounting. Diving in a little bit more and sharing kind of what's going on behind the scenes of our infrastructure, the graph on the left is how we visualize all of our EC2 usage. We leverage the tagging system on EC2, so I can create these split charts to see what kind of workloads are we actually spending money on. I really like seeing the blue, so both Mesos and Kubernetes we're using heavily. Mesos we're using for some of our data loads, which could be another talk at a different time. And then we see that huge chunk designated to Kubernetes. And on the left side of that chart, we have other infrastructure. As Hubert mentioned, we've elected to keep out of our Kubernetes cluster, like our high availability key value database, HDFS, some of our analytics systems, Kafka, and some other core infrastructure. On the right is a chart that I derived by exporting the previous slide's information, where I'm able to visualize point in time what's the distribution of our workloads. So this was plotting the actual CPU cycles by how they were purchased. And this is a chart that I always like to keep my eye on, in that I want to make sure that we have a good chunk of RIs, or reserved instances, because a lot of our Kubernetes clusters we know are always going to be at least, let's say, 100 or 200 nodes. We have a pretty good chunk of spot instances, which again, Hubert described, we can do that automatic scalability. So if at 1 in the morning I needed to provision 10 more machines, we'll pull them from the spot market. We'll be paying, what, like 6-7 cents an hour, and then they'll get added to the cluster. And then when we don't need them anymore, we can scale them down. And then we also have some amount of on-demand. I wouldn't recommend doing 100% RIs, because again, sometimes your workloads will go up and down. And in fact, as I alluded to earlier, on a day-over-day basis, our workloads and our clusters grow and shrink automatically depending on the traffic to our platform. So I think one of the really great concepts that we are able to leverage because of Kubernetes is this idea of a general compute platform. So for the developers, they just see this platform that says, let's say, 1,200 cores. But under the hood, it's actually a heterogeneous compute pool, in that we have nodes of various different sizes, of various different instance classes. We have M4s, we have C4s, we have C5s, and we have a bunch of other instances. This is really great from a provisioning perspective. This gives you a path to upgrading family instance types. So let's say that I did a 1-year reservation of M4s, and then Amazon announces that they have these really amazing M5s. I don't have to think, oh my gosh, how am I going to move all my workloads from one to the other? We just throw them all into the Kubernetes cluster, and then the developers don't even know that's happening underneath their feet. This has been also really helpful because we are using spot instances. The spot instance market is kind of like this game system where maybe we can't find any M4s in the spot market, but we can find a ton of M5s or a ton of C5s. We can add those to the cluster, and we get the nodes that we need at a really great price. Great, so we're coming up on just 2 minutes left. I wanted to summarize a couple things and go over some of the key challenges that we talked about at the beginning. So the first challenge that we described we wanted to have a solution to was, how do we solve this general compute problem? How do we decouple the developers' needs from infrastructure and operations needs? And we achieve this with Docker, with Kubernetes, and our auto-scaling. And then how do we manage our costs in this environment? I just described how we leverage a blend of on-demands, spots, as well as reserved instances. So going back to that first high-level architecture that I showed, what we've been able to achieve at Branch, and this is how we've really scaled both in terms of the scale of the infrastructure, but as well as the scale of the costs. At the very top, the developers' concerns are all being met because they can deploy a variety of different workloads and applications into production. We have JavaScript developers, Python developers, Java developers, each one of those applications might require a small or a very large footprint. We have various different Kubernetes production clusters that offer these cores so that they can satisfy the developers' needs. And on a day-to-day basis, when our developers say, hey, I thought I needed 300 cores, I actually need 350, they don't even really need to interact or ask the infrastructure team from a capacity planning and capacity management perspective. This is all within their control. And then again, we've separated that core compute platform from the capacity and kind of price modeling perspective. So at the very bottom, I spend a lot of time working and modeling with our finance team, and they're very aware of on-demands. They're very aware of RIs, but they have no idea what a 10-core Node.js application is going to cost, and they don't really care. And realistically, they shouldn't. So we've created these kind of 3 layers of abstraction, which allows each functional group within the organization to be successful and optimized within that particular domain. Great. So that concludes the talk. I think we're going to go to questions in this app, and then we'll take some questions from the floor afterwards. But before we do that, I just wanted to thank you all for your undivided attention, and it was a great pleasure to be here. Cheers. OK, yeah. So the question was, do you periodically rebalance pods to restore a somewhat even distribution of them across the worker nodes? If you do, how do you do it?
We don't actually have to do that generally. There is a project called the Descheduler, or which tries to do that. But the reality is, when you have 100 nodes, the balance is probably not going to get much better or worse when you if you try and rebalance it. So not that much.
Cool. Oh, you don't want to do it by popularity? I mean, the features there. Great, cool. Second question was, are you running your own Kubernetes on EC2 or using ECS or EKS?
We run our own Kubernetes on EC2. We're looking at EKS. We'll probably do some of those.
And I think Hubert mentioned it earlier on. We were running Kubernetes in production about 4 years ago, before EKS was a thing. I know ECS was an offering that we looked at, but we've been very happy with our management of Kubernetes right now.
And one of the other things that Kubernetes gives us is sort of cloud agnostic capabilities. So for flexibility, now we could deploy Kubernetes into GCP, of course. They have probably a stronger Kubernetes offering than AWS. And also, if we were ever to go into Azure or some of the other smaller platforms, Kubernetes gives us an open platform to be able to do that. So that was one of the strong considerations when we chose Kubernetes over ECS.
Next question is, which programming languages did you use for developing microservices? So at Branch, our 2 primary first-class languages are JavaScript and Java. The original Branch core application was a gigantic Node.js application. And then we started carving it out into JavaScript microservices. Then we started building RESTful Java services. We also have some Python services in production. We have quite a lot of Lua in production as well. But again, using Docker and deploying to Kubernetes, for the most part, operations is agnostic to what languages our developers are writing them in. Next question is, do you use Alpine Linux for your containers?
We don't generally build Alpine Linux containers. Third parties tend to do that. Running Alpine is something that an optimized workload might do for extremely small memory or CPU footprint. That hasn't been a primary concern for us. We tend to like developer tools, so we haven't optimized for it. And I could see us doing it in the future for security, but right now we haven't.
So next question, if EC2 is such a large part of your AWS bill, what are you doing for databases, running them locally on EC2 instances? So yeah, EC2 is a pretty big chunk of our bill. We do use Amazon's RDS for things like Postgres. When I showed that split of our overall bill, about, I think, let's say 70% of it was EC2. And then when we dove into where's that EC2 spend going, half of it was to orchestration frameworks like Mesos and Kubernetes. And then the other half was designated to things like Druid, which is our columnar analytics database, Kafka, which we're using comprehensively throughout our infrastructure. And then we have a combination of Aerospike, which is a extremely high-performant key-value database, as well as DynamoDB. And we actually were here about 2 months ago, and we did a talk about our usage of DynamoDB, so you can check out that talk as well. The next question is, interested to learn during your talk if you're using AWS App Mesh, and if not, what are you doing for Service Mesh to link microservices?
We're not using it at Mesh. It's brand new, so we haven't yet tested it. Service Mesh is one of those things that's very high on my list of things to do. I have tested Istio. It was more than a year ago, and it was a little rough, so I didn't feel like putting it into production, but I think now it's made enough progress. The other consideration is I'm looking for a solution which runs not just in Kubernetes, because we have a large non-Kubernetes infrastructure as well, so something a little bit more generic. Istio is great now for within a cluster, but we need something that provides both multi-cluster and non-Kubernetes support. So that's one of those investigative areas. Likely we'll choose something like Console, or App Mesh is a consideration, or we could also use Envoy directly.
Next question is, do you have DR for EKS across multiple regions? If yes, how do you achieve that? So as Hubert mentioned, we're not directly using EKS right now. We deploy and manage our own Kubernetes clusters. We don't deploy those clusters to span multiple regions. That would potentially introduce quite a lot of potential latency and network transfer concerns. Although we do have a DR Kubernetes cluster running in our failover region in US East 1. But currently we have all of our primary production clusters running within our primary US West 1 region. I'm actually not too familiar with setting up EKS across multiple regions, but that would be an interesting experiment to hack on. What tools do you use for monitoring Kubernetes itself?
Primarily, everybody in the Kubernetes world uses Prometheus, and we've adopted that. It took us a while to get it stable, but it's actually very, very scalable. In highly dynamic environments, it provides a lot of features around service discovery that are really hard to replicate in other environments. So I strongly encourage everybody to look at the architecture of Prometheus. It's pretty good.
Cool. This question I think came up earlier too, but if you run your own Kubernetes rather than EKS, why not use AWS EKS service? So Hubert mentioned earlier, it is something that we are going to investigate and evaluate. It did not exist when we started using Kubernetes. We were actually, I think this was like 3 years ago when our office was down in Palo Alto. We worked pretty closely with Google and the folks that were developing Kubernetes at the time, and they were excited that we were deploying this to production. And I think with the developments that have been made with AWS's EKS, this is definitely something that we're going to explore. Do you have any experience with AWS COPS? Can you elaborate the choice between EKS versus COPS?
So as we mentioned, EKS wasn't a thing when we started. It was COPS. That was all. And we still deploy with COPS. COPS is good. It has better flexibility, better control if you want that. If you want to not worry about it, EKS is probably better. If you want more managed-ish, then EKS gives you better, you don't have to worry about as much. But if you need certain features, like if you want to run the very latest version of Kubernetes, or actually COPS doesn't provide the very latest either, but if you want to run like custom code inside the control plane, or want to provide other types of CNI network interfaces, then COPS is probably the primary choice I would use in AWS.
Next question is, do you use the upstream or custom DNS for servers not resolvable by Kubernetes' own DNS?
So Kubernetes runs its own internal DNS, and then it forwards to the external DNS, which by default in Amazon is the Amazon DNS. And that's the standard, and we use that. So we don't, all the hosts inside Kubernetes just resolve. They try to resolve within the cluster, and then when they don't, they try to resolve through Amazon DNS, and that's fine.
So on costs, the next question is, did you calculate your man-hour costs, salary, and benefits to run Kubernetes versus using a managed Kubernetes service? A lot of EKS questions. Yes, I have done these models before. It is certainly going to factor into our decision to consider EKS. One of the challenges is I don't believe EKS is available in every region yet, but that'll definitely factor in. I mean, if it's not available in the region that we need it, that would be a blocker. But absolutely, now that a lot of these managed services like EKS and managed Kafka, for instance, have come up, it's certainly one of the considerations that comes onto the table. Now, mind you, the EKS service isn't necessarily going to be at the same price point as a hyper-optimized Kubernetes cluster running on spot instances. So there are some trade-offs there that have to go into that calculus as well. Next question is, what is your ratio of developers to DevOps? So we have a relatively small and lean infrastructure and operations team. It's effectively our DevOps team. So with about 75 engineers, we have seven, so it's about 10 to 1 right now. And I would definitely believe that the functionality and some of the capabilities that we've been afforded with things like Kubernetes has helped us keep that ratio. It's also worth mentioning and repeating what Hubert mentioned. The developers are all like super pumped and jived about using Kubernetes. They're managing a lot of their own services. They're taking care of a lot of their own services. They're provisioning and scaling their own services, which makes our lives a lot easier. But that's like a huge benefit to, let's say, in a different world or in a different environment. It would be very unlikely that somebody that's managing, let's say, a 50-core node app to necessarily provision their own capacity and scale it out by themselves. Next question is, do Spark jobs run well on Kubernetes?
So we do run Spark in Kubernetes. It's pretty successful from the standpoint of just straight compute on top of instances. The areas where I would caution about it was, so if you have Spark jobs that talk directly to storage, like you typically run Spark on your Yarn on top of HDFS, that's a little bit dicier. I probably wouldn't do that. Our Spark jobs are typically reading from like an S3 or something else, external storage. So if you need high performance to co-locate your compute on top of your storage, like they do in many Spark environments, it might not be appropriate. There is new native Kubernetes support that does that. We don't run that. We essentially run Spark standalone clusters inside Kubernetes, which works fine with the caveats that I just mentioned.
And I think we have time for like 2 or 3 more questions before they kick us off the stage. So if we don't get to your question, I think we're going to hang around for a bit. We'd be happy to answer them. But I'll dive into this. I keep getting flashed like a sign back there. And they're like, yeah, hurry up. OK, next question is, how are you hosting your images?
We have our own Docker repo that we host on an EC2 instances, and it works fine. It's just a Docker registry running inside Docker, not inside Kubernetes. We have too many clusters, so I don't really want to run the Docker registry inside the Kubernetes. But some people do it. I've heard success stories with it. I don't.
Do ML jobs using TensorFlow run well on Kubernetes?
We haven't done any TensorFlow on Kubernetes. We don't actually do any TensorFlow at all. So
yeah, we're like, this is the startup talk where we don't say machine learning and we don't do any crazy AI or blockchain. It's just crazy scalable infrastructure. Sorry, guys. OK, you talk more about network issues you've seen and how your networking is set up, VPC for all cluster or per cluster, et cetera.
We started out using this default configuration was a new VPC per cluster, but then the network transfer costs are pretty daunting actually. So we're moving some of our network back into our standard VPC. So it is one of those costs we actually do care a little bit about because we're doing so many analytics types of workloads, pulling from Kafka. All those things add up not just to compute, which doesn't matter what network you use, but the network transfer cost does add up. So we've been migrating some of our workloads back into our primary VPCs.
Do you use any specific tools when it comes to infrastructure as code, like Terraform or Helm?
We haven't. used Helm much. We've looked at it. We may in the future use it. A lot of the infrastructure we built is 4 years old, and I would like to get rid of it. But at the time we built it, we didn't have the tooling really wasn't there. So a lot of it's handcrafted, and you could use an update. So Terraform is another, similarly, there was not really Terraform support, but nowadays, if you were to build a COPS cluster or build an EKS cluster or build a network, you could Terraform all of that. But at the time we started, those tool sets around Kubernetes infrastructure weren't available.
And I'm going to keep going until they kick us off. But if you have to get out of here, just by all means, just leave. So how do you handle spot instances being ripped from your arms?
So
well, we should do like a whole talk on that. Like, it's like, yeah.
So the primary thing is to make your app stateless. So spot instance dies, just spins up somewhere else. The secondary things are you can force scheduling onto on-demand instances. So there's primitives around that. So on-demands won't get taken away. You never have to worry. For critical workloads in high SLA type of environment clusters, we'll do that. We'll either put you in a high SLA cluster, which we use all on-demands and say you'll never get rescheduled unless your application does it. Or for other types of workloads, like if it's a Spark job, we're relying on you to build a resilient application such that you lose a spot, it is generally unaffected. And
we're officially getting the time. So once again, thank you all so much for attending our talk. It was a pleasure, and we'll hang out for a bit afterwards.